Okay, so we've moved from the notion of complex algebra into studying the idea of complex valued functions. So when studying complex valued functions, one of the main things that we need to just even begin with before even starting our notion of trying to extrapolate calculus to the complex plane, we need to just even consider what complex functions would look like. So we're going to start Unit 2 by discussing a class of functions in complex analysis called the analytic functions, which is the title of this unit, and we're also following Safin-Snyder's nomenclature, so we are also looking at analytic functions for this unit. So let's consider once again what a function is. I'm sure this is something that everyone's done in either 8th grade, 9th grade, or 10th grade, but just considering what a function is in general. Of course, we'll use some more nuanced nomenclature and symbols to describe it, but in general, we're considering, once again, the same thing. Now, F is a mapping between A and B. Now, this is something that just defines a function such that for every input, we have one output, and there's no restriction on how many for every input, we have one output, right? The vertical line test allows us to determine whether a function holds or not, is the definition that you get typically in high school. So we consider a mapping from A to a mapping B, and this function takes us between A and B. So we take an element in A and it transforms us to an element of B such that f of A equals B. So this is a notion of a function. It's pretty simple, and you covered in calculus. That's the study of single variable functions. Cover the notion of multivariable functions. Then complex analysis, we go to the notion of complex valued functions. So instead of having this be called x and this be called y, we transition to call this z and this called w. So we have a z space and a w space in complex analysis. So if w represents the value or the image of the function at some z, then we say that w is equal to f of z. Now we need to be very careful about what we're considering f of z to be. In complex algebra, we've always defined z to be equal to x plus iy. So z itself is a function of x and y, so we need to be careful of that and then represent w as some function u of xy, which represents this x part, plus I times v of xy, which represents this y part. This is the convention we're going to use, that u is the x, or the real component of the function, and v is the complex, or the imaginary component of the function. Important to note is that these are both multivariable functions. U and v are functions of x and y. They all go into w. So you can imagine that this makes things quite tricky to visualize. So actually visualizing complex functions comes out to be more of a mapping between some z space, which is a complex plane itself, over to w space, which is a complex plane as well. So you're taking points and you're moving points around. Essentially, so the way to see it, a lot of people visualize this by using color. So z space will be a colored map of R2, and W space will also be a colored map of R2. But it's very impractical to actually visualize complex functions, so it's usually good to take multivariable calculus before complex analysis, just because you can envision what a lot of the functions will look like in multivariable calculus and get to know how partial derivatives work and how integrals work before moving over to complex analysis, where you still need to use all of that stuff, but you don't really know what any of the stuff actually looks like. So it makes it a little bit more tricky. So as a part of our introduction, let's just do a couple of easy examples just to visualize and describe what complex functions might look like. We're not going to spend a lot of time on this because I find it to be relatively trivial and not a good use of our time, but we will discuss it just briefly. This example is Saff and Snyder's example 2.1.1, and we would like to write the function w equals z squared plus 2z in the form of w equals u of xy plus iv of xy. So what we're going to do is we are going to write this out in the form that z is equal to x plus iy. So when we do this, we're going to set z equal to x plus iy, as I said, and then we're going to get w equals f of z, right? And now we're going to plug in x plus iy wherever we see any z's. So we get x plus iy squared plus 2 times x plus iy. And when we do this, we are going to FOIL out to the first one. We remember how that works. We get x squared minus y squared plus 2ixy. And then we just distribute, getting 2x plus I times 2y. And now it's only a matter of factoring by grouping, and taking in the real and imaginary parts and putting them together. So therefore, we find that w is equal to x squared minus y squared plus 2x plus I times 2xy plus 2y. So therefore, we've transitioned this function in the form of z into something that I would call more like a standard form of f in terms of x and y. So I would hope that this makes sense to everyone, and this is sort of how it works. Okay, so now let's do another example and actually trying to figure out what these functions really kind of look like or what they kind of do, if that makes any sense. So this one is from Saff and Snyder 2.1.3, and for this we want to describe the function f of z equals z cubed for z in the semi-disk given by z modulus greater, or z modulus less than 2. Okay, and imaginary of z is greater than 0. Okay, so we need to draw this out. It's usually almost always helpful in math to draw things out. So we are taking the area in this disk, z equals, so this has a radius of 2, so call that 2. And then we're also taking that the imaginary part of z is greater than 0, so that immediately gets rid of all of this crap. So we don't need to deal with any of that, so we're only dealing with the semi-disk. So the easiest way for me to explain how this works is by using de Moivre's theorem. So I'm going to give an analytical explanation, and then I'm going to give an explanation purely by words. So I'll show the one by words, and then we'll look at the other one. So we know that points in the section of the disk between argument of z equals 0 to the argument of z equals 2 pi over 3 when cubed are going to cover the whole disk with the modulus of w less than or equal to 8. Now, why is this? So the way that we look at this is by using de Moivre's theorem. This is a very important theorem that helps us visualize a lot of stuff in complex analysis. Remember that z to the n is equal to r to the n times cosine of n theta plus I sine of n theta. And what we're going to do is we're going to set n equal to 3. So z to the 3 is equal to f of z, first of all. So it's really important to know. R cubed. So this r cubed at the front is explicitly going to tell us that our new modulus at f of z is going to take the old modulus at 2 and bring it up to 2 cubed. So we're going to have a new modulus at 8 because 2 cubed is equal to 8. And that's what de Moivre's theorem tells us, because it tells us that z cubed is equal to r cubed times some other stuff with the trig functions. We'll deal with that later. And this has a radius of 8. Now we see that we're taking cosine of 3 theta plus I sine of 3 theta. And we note that if I have this theta here at 2 pi over 3, we are going to be going up to 3 theta. So what this means is if I'm at 2/3 and we're going up to 3 times 2/3 of the unit circle, we're going to go all the way around the unit circle. So from 2/3 pi plugging in the function with de Moivre's theorem, we're going up to 2/3 times 3, which is 2 pi. And then if we take it a step further and go to pi, then we are going to go up to 3 pi. So if we, so this sort of explains that, and we know that the sector of the disk from arg z equals 0 to arg z equals 2 pi over 3, when cubed, will cover the whole disk with w equals 8. The other points are going to, again, be shifted even farther. They're going to go all the way around.